Lucia Gaucia, and let me get to my slide first. And my research is focused on the mobility of batteries across lives and across applications. So batteries have different lives. A first life, for example, is in an electric vehicle, which is a pretty demanding application. Once the battery reaches the end of life, there is actually around 70 to 80% of remaining capacity in the batteries for a second life in a more gentle application, like, for example, grid, residential, or commercial. To do that, what we do is we take the battery cells that are in the vehicle, we grade them depending on their aging, and then we repackage them according to their aging to be used in second life applications. To do that, what we are having is a problem that is very similar to ecological problems, because we are having individual battery cells that are grouped by populations, and they migrate from one application to the other in different aging stages. We also have similar comparisons to ecological systems, because we have aging dispersion in those populations, and also we have from incomplete data to no data at all of knowing what that battery did in its first life before it moves into a second life. The work that we're doing now has just been recently funded through an NSF Career Award. So to be able to do this ecological parallelism, so that we can maximize the life of a battery, not only at first life but also at second life, we need to be able to do very large testing. We're going to emulate first life and second life by using, by using mini labs, where we're going to test in a very low cost and real-time way first life and second life of new and used batteries, and we're going to do it in different scales, individuals and populations through the modules. We're also going to study environment variations to be able to see the whole spectrum of applications that a battery can work on. We're going to have students interact with our mini labs through Ethernet, so that we can increase education in energy storage in different types of applications. The objective of all this testing is to be able to populate some causality networks that consider not only data for a single battery, current, voltage, and temperature, but actually data from the ecosystem or subsystems that is surrounding the battery, and that they will have either a direct or indirect impact in the battery operation. The objective is for this data to be gathered from sensors that are available in that life, and for the battery management system to learn those networks and to construct them and to adapt them as the battery moves from one life to the next, so that we can maximize the usage of life in that application, and we can also maximize safety. In the end, we want to formulate multi-scale theories where we consider two scales: time scale from first life to second life to consider the whole life cycle, and also population scale, where we go from an individual cell to a whole battery pack, and how do they work together. So to do this, we are going to also be using real-life testing data from vehicles in from General Motors that are available in the APSRC, and we're also going to use data from a utility company that has a PV battery system, and we will be using new and used batteries. We also have some academic collaborations in different departments to bring together computer science, ecological theory, so that we can improve the usage of battery. Thank you very much.